So today we are going to talk about the discrete signal processing Z transform, which is the lecture 10 out of the signal system 11 lecture. And now we are going to talk recall from last lecture we know what is Laplace transform, and which is calculated in this formula, and we can calculate the transfer function, which is just the Laplace transform of the impulse response ht, and we can just calculate ys, which is equal to the hs times the xs. And in this lecture we're going to do discrete time signal processing, the block diagram, and the Z transform. So the continuous and discrete time is just like what if the input is continuous time, the output is a continuous time, and what if the input is discrete, the output is discrete, then it's a discrete time system, and then it will have the corresponding hn rather than ht, right? So the discrete time system, we're going to learn the impulse response for the discrete time system, and what is the transfer function, what is the Laplace transform, since the Laplace transform only works for the continuous time signal because it is an integration. And in the discrete time, we know that the derivative can be 导数可以看成差分啊 ，integration can be taken as a summation, and so firstly, what you will see the difference equation, which in Chinese is called 微分方程, which is the behavior of a continuous system, be actually described in the differential equation, like the charging capacitor is a transient, and so forth. The discrete time system can be described as a difference equation. The first one is the differential equation, right? The second one is the 差分方程. Okay, so the good news is that difference equation is easier to handle. And the discrete time processing in the digital signal processing is the input is a series of values arriving to the discrete time intervals, and they are manipulated in the discrete time signal processor, which is yn equals to fn, fxn, xn minus 1, y minus 1. This construct using a basic operation, maybe a time delay, addition, subtraction, scaling, and summation of intervals. So another thing is about the block diagram. For convenience, the simple processing operations are often represented as graphically as a block diagram. So for example, this one, look that in this one it's delayed by delayed by a time interval, by a period, and this is add constant to the signal, and this one is actually scaled by a signal, and this one is make a summation for both of them. It is worth noticing that add is only at a constant, and summation is adding some variables. And another thing is about parallel and cascade. The parallel is this one, and the cascade is this one. It's just like in Chinese it's called 并联和串联啊。And for the cascaded system, we can first go to a system, go to convolution with the second one, then convolution with the first one, or we can first convolution with the first one, then convolution with the second one. I mean, they are all the same, equivalent. Okay, additionally, we are going to know the corresponding transform in the discrete time, which is called the Z transform, and which is calculated in this formula, which is summation from 0 to infinity, just like the integral from 0 to infinity, xn times z to the power minus n. and it's a convenient and powerful theoretical tool to representing and analyzing the discrete time signal system. And this is a similar role for the Laplace transform, and the relationship in Z is just like it's a Z domain and S domain, just like in different domains. And for the continuous time, we have the xt as input. For discrete time, we have xn as input. For the continuous time, we have the yt as output. For the discrete time, we have the yn as output. And the impulse response for the continuous one is ht, and the impulse response for the discrete one is hn. The transformation for the continuous one is the Laplace transform, and the transformation for the discrete time is Z transform. The continuous time will integration from 0 to infinity ht times e to the power of minus st dt, and ht and the Z transform will be hz will be summation from 0 to infinity hn times z to the power of minus n. And the corresponding transfer function for the continuous time is hs, and the discrete time is hz. So now we know that for the signal, everything can be classified as signal and system in this course, and for the discrete time and continuous time is just this basic 4 domains. So this is not covered, which is called discrete Fourier transform series, and this one, what if it is periodic, it is a Fourier series, and what if it is not periodic, it's a Fourier transform. And for the systems, we are going to do the Laplace transform for the continuous one, and for the Z transform for the discrete time. And the two-sided Z transform, just like the summation from the minus infinity to infinity, and the single-sided Z transform is from the 0 to infinity. And there are some Z transform pairs where xz is summation from the xn times z to the power of minus n, and this table will be given in the final exam. For example, the sequence for the delta Dirac function is the corresponding Z transform is just 1, and the correspondence Z transform for the unit step function is Z divided by Z minus 1, and b to the power of n, the corresponding Z transform is Z divided by Z minus b. So another example is to find the G transform of the discrete delta Dirac function, this one. So the thing is that since this is only evaluated at 0, which is infinity, so this is just the summation z to the power of minus 0, which is 1. So the final answer is 1. And we can just find the table. And what if it's z minus 1, then let's only look at what if it's z to the power of minus 1, okay? And what kind of the G transform of the xn equals to Z transform of xn equals to 1, 2, 3, 4, 0, 0, 0, 0. So this is a very interesting one. So let's talk about starting from n equals to 0, xn equals to 1, 2, 3, 4, 0, 0, 0, 0, starting from xz. Let's just substitute the xn into this summation, and for example, is 1. It is worth noticing that n always starts at 0, and so this way is corresponding to n equals to 0. Therefore, it's 1 times z to the power 0 plus 2 times z to the power minus 1, and z to the power minus 1, and 3 times z to the power minus 2, and so forth. That is basically the correspondence. And the time delay one is just like, what if we are delaying in the frequency, or in the time domain, we are going to have a corresponding z to the power minus a in the frequency domain. So what if we have this kind of thing? We can know it's just like delayed by some number of samples. The transfer function xt is going to change into the ht, and the yt is xt convolved with the ht. The ys is just the xs times hs, and correspondingly we are going to have in the z domain we are going to also have the transfer function rather instead of s, and similarly we can also do the cascade system in the Z transform. Okay, let's talk about the recursion and feedback. Find the transfer function for the following feedback. So it is worth noticing that this one is kind of a recursion where it is calling itself again. So how do we deal with that? So we are going to do the G transform for, as we know, the Z transform for delayed signal. It is just the a y z z to the minus 1 x z and this. We are just going to substitute get out the yz and to get the corresponding hz, so which is defined as yz divided by 1 divided by xz. Therefore, it is illustrated here. So in these cases, we have we are going to form a block diagram to see what is the corresponding transfer function. This is very interesting. That firstly, here we are going to scale them by 2, right? So here we have the 2xz, right? And then we have the this is just like so this is minus z to the power of 1xz. And then for here, so this is this one, this is this one, this is this one, and this is this one. Okay, this is yz, and another we are going to yz times 1 divided by 2 z to the minus 1. Okay, together we're going to get yz. So this is just and based on that we're going to just substitute the yz together, xz together, and that's all. Thank you very much. Welcome comments.